Let's continue in 2.1 and take a look at theorem 2.1. So let's let W be a subspace of Rn. Okay, so subspace, just to recall, means that for any vector in W, for addition and scalar multiplication, it remains in W. So then we have that a subset of, so a subset, well, actually, a subset that looks like this, a subset W1 to W sub K of Rn is a basis for the subspace W if and only if you have two things hold. One, W1 to W sub K span W, which makes sense, right? You gotta, all linear combinations make up all of W. And two, for it to be a basis, the vectors are linearly independent. The vectors are linearly independent. And that's something we've already seen. Like, you can't have redundant vectors that are made up of scalar multiplication, or that are made up of linear combinations of another vector. Okay, that's the key there. This is often, in many books, the definition of a basis. So we often see that this is a basis if these two hold. This book chose to do it a little differently, and they explain why. It has to do with the definition of basis we did, where the only way to get the R, just to be clear on this. So this book uses this concept that this is a unique linear combination. So to get 0, you have a unique linear combination for every vector. And it kind of ties into linear independence as well. All right. The next property or procedure I will copy in, it's on finding bases for a set. So this is, I have this down here, a little example. So go ahead and speed this video up a little bit. So copy this in, or as you go here, I'll go ahead and shrink it down. Fits. Okay, so this is the procedure we do to find a basis for W, which is the span of these vectors. So if you have just a bunch of vectors and you want to find a basis for W, this is what you do. And we've already done this, basically. You form the matrix where W1 through W sub K are columns of A. You row reduce. And then the set of all column vectors, this is a column vector, that contain pivots basically on the diagonal, right, is a basis. So if it zeroes out, you're not going to include it. So here here's an example. So you form, so here's your vectors, W1, 2, and 3. And you form your matrix, and then you row reduce. And you can see you get this vector and this vector. These have pivots. So 1 and 1 are the pivots. Nothing zeroes out. And so these two vectors, the given vectors, would form a basis. So you choose just W1 and W2 for your basis. So that's the technique. And we've basically seen that before in different ways. Okay. Let's look at the next definition. So this is definition 2.2. And it's really just how to define dimension. So this is definition of dimension. So definition, like of a basis. 2.2 says this: let W be a subspace of Rn then the number of elements in a basis W I should say basis of W. In a basis of W is the dimension of W. So is the dimension of W. So like how many vectors does it take kind of thing. And we'll denote it. So and is written denoted dim W. Okay, so let's take a look at this one. So find the dimension of the subspace defined by S equal the set of these vectors 1, -3, 2, 2, -5, 3, and 4, 0, 1. Okay, so what, just to describe this, what set are these in? What's the big set? Those are an Rn, right? Because there's 3 elements per. So that's in R3. So basically what you're doing is you're seeing whether any of these vectors are linear combinations of each other. So if you get basically a 1 and a bunch of zeros and everything else zeros out, that means it's all the same plane, essentially. Or you could get 2 of them to be linear combinations of each other, and then this would be dimension 2. So that's really what you're doing. So the technique is that we already did 1 basically, or I showed you 1. So if this was a 1 here, then it would be dimension 3. Okay, but this only has 2 elements in the basis, so that's dimension 2. So that's how you basically look for it. Okay, so let's go ahead and write that out. So you form your matrix just like it says. 1, -3, 2, 2, -5, 3, 4, 0, 1, and then you reduce that. And you can do everything on a computer or calculator. And you get the identity matrix this time. So you'll get 1 0 0 0 1 0 0 0 1. So each row contains pivots. Each column is pivot. So you look at that diagonal, and then pivot, pivot, pivot. So there's 3 of them, and so the dimension is 3. So therefore, the dimension of S is equal to 3. And we also, so the span of these vectors form S, and it is a basis. So these 3 vectors form a basis. So we can say, and all vectors are linearly independent. Okay. Next theorem. Let's see what we got here. Let me clean this up a little bit and move this over. So let's see, that's equal to that. This is theorem 2.2. Okay, so this has to do with dimension of subspace and stuff. So let W be a subspace of Rn. Let W1 to W sub k be vectors. In W that span all of W. Let V1, oops, a little quick there. Let V1 to V sub M be vectors in W that are linearly independent. So be vectors in W that are linearly independent. So we're comparing the number of vectors. So we're looking at that this is M that are linearly independent, but we know that K vectors span W. So our conclusion then would have to be that K has to be greater than or equal to M. So if it can't be the other way around, right? I mean, you can't have these linearly independent and have a smaller number of linear independent vectors that span the set. So this is our conclusion that we can come up with. Now, the corollary is using and putting this all together and basically says that this is the kind of what we can use. So the result of this theorem says that the number of elements in a basis have to be the same. So bases contain the same number of vectors, or the dimensions the same. So a corollary to that theorem says basically that bases contain the same number of vectors. Okay, so we may be applying that later. All right, so next theorem 2.3, We basically need to develop a bunch of stuff before we can do more, is essentially what we have to do. Okay, is the existence and determination of bases. Yeah, and so this one basically clarifies a bit of things. So let's take a look. Oops. Let's see. Where did that go? Little pause here. Look up 2.3 if you have your book out. Let's do this one. I had to mess something up here. Okay. So 2.3, this is on existence. And determination of bases. So 1, every subspace W of Rn has a basis of dimension W less than or equal to n. Okay, well that's got to make sense. It can't be greater than n, right? So you take every subspace of W and you have Rn. The basis dimension must be less than the big set. Now you can have a set of vectors that span Rn, but are not necessarily linearly independent, but that would not be a basis. Okay, 2, every independent set of vectors, so every linearly independent set of vectors in Rn can be enlarged. Oops, wrote that backwards. Can be enlarged if necessary to become a basis. That's where I always mess up the spelling when we're going fast. Basis. So that, for Rn, sorry. For Rn. And basically, this one's kind of silly. I mean, basically what you're doing, you're just going to add e's. So you figure out which vectors to use, and then you just add a couple more. We're going to do one, but... And then 3, okay, is this one. This one's probably more important to try to comprehend. If W is a subspace of Rn, and the dimension of W is equal to K, then every independent set of K vectors in W is a basis. Then every linearly independent set of vectors, set of K vectors, K, like the same number, K vectors must be a basis, right? And W is a basis for W. The key is that they're linearly independent, right? I mean, they're an independent set of vectors, and it's the same number of them, right? So that's relying on this concept up here. It's the same number of vectors. And they're linearly independent, so it has to be a basis. And B, every set of k vectors in W so every set of k vectors in W that span W is a basis for W. Because remember, the vectors in W, excuse me. So every set of k vectors, so it's this number of vectors that's kind of important here. So there's k vectors in W, and it spans all of W. Then it must be a basis for W. Okay, and I know there's a lot going on here. You got to start piecing together, but okay, so we'll look at another few examples, and that'll wrap up 2.1.